Okay, well, let's go through the notes so far in the corrosion topic. So hopefully you've got these notes in front of you, and let's add in the information. Okay, so corrosion. Corrosion is. Now what you've got to do here is you have to put the definition of what corrosion is. Well, corrosion is the oxidation reaction that happens on the surface of a metal, turning the metal atoms into metal ions. Okay. State the chemical equation, and then you've got two examples. Well, as you see there, it says copper solid. Now, copper does corrode, and when it corrodes, it loses electrons, hence the whole oxidation reaction part of the definition. So copper, now it's a transition metal. Now transition metals are called the transition metals because their valency can change. So copper could become Cu plus or Cu2 plus. So most commonly, I'm trying to think of things my class would see. Most commonly, you would see this forming a Cu2 plus ion. So therefore, Cu2 plus would go there, plus 2 electron minus. Okay, now trying to make this make sense to you, what that's saying is that if you've got a copper atoms, okay, so say that was like a copper pipe, fresh, brand new copper pipe, it will corrode, and when it does so, it loses electrons. That's why they're on this side. And when it has lost electrons, it started off neutral, and because it's lost something negative, it becomes positive. So it'd be Cu2 plus 2 electrons. Now, if you've got it written as changing into Cu plus, then I'll still accept that as an answer. So you could have copper solid changes into Cu plus an electron. That would also be totally acceptable answer as well, because like I've said, copper is a transition metal. Now iron, another transition metal, it can form a 1 plus charge, 2 plus charge, or a 3 plus charge. So really, what you should have here is you should have Fe, a number there, right? I'm going to put it as an X plus, and a number here for the electrons. Now that's my fancy way of just showing you that you can have, I'm trying to make my pen a little bit better, you can have multiple acceptable answers. So you could have Fe changes into Fe3 plus 3 electrons. Okay, so whatever number you've got there, that's the same number that you would put there. Now, if you've watched the video on the NACE Foundation video, on YouTube, you would have seen so many examples of problems caused by corrosion. Literally, planes can fall out of the sky, bridges can fall down, boats can sink, the rebar that holds the road together can rust, and therefore the road can fall apart. And you know, there's lots of compelling reasons to understand why we should care about corrosion. So by watching that video, hopefully you've got a list of examples of things, examples of problems that can occur that you've got written in that box. Okay. Now, what causes rusting, the corrosion of iron? Well, as it says here, rusting is the corrosion of iron. Rust is a common name for the red flaky coating formed on the surface of iron. It is a compound formed when iron corrodes. Record the results of the experiment set up to investigate what factors cause rusting. You may have taken part in the home experiment where you put nails into rice or salt, one where you had boiling water with oil on top, and one where you've got air and water. Well, let's just go through this, right? So in this one here, this test tube here has calcium chloride. which you may have used rice at home. It's calcium chloride is hygroscopic, sorry, so it absorbs moisture. Okay, it's a desiccant, just like rice is a desiccant. So therefore, by absorbing water, this nail is only exposed to air. This test tube here has a nail which has been placed in water which has been boiled. And through the process of boiling water, you actually reduce the concentration of oxygen in that water. You'll not completely eradicate the oxygen in the water, but you'll greatly reduce the amount of oxygen in the water. So this test tube here is water and no air, well, very little air. The reason why oil is being placed on top is it's a barrier which, because of its thickness, it's very difficult for air to pass through into the water, and so therefore the diffusion of oxygen into the water is decreased because of the thick, dense oil. The last test tube has a nail in air and water. So in test tube 1, the calcium chloride absorbs, well, it absorbs water. So the nail is only exposed to air. There was a bit of a problem with the recording of the video there, so I'll just make sure I clarify everything that went on before the video stopped recording. Test tube 1 contains calcium chloride which absorbs water, so the nail is only exposed to air. In test tube 2, the nail is exposed to water but not air. And in test tube 3, the iron nail is exposed to water and air. Now, of course, the part of air which is important in rusting is the reactive part of air, which is, in this situation, oxygen. So really, for iron to rust, you need water and oxygen. So after a few days, rust formed only in test tube 3, where the iron was exposed to both water and oxygen. I'm going to put oxygen there. You may have put the word air there, that's fine. But I'm putting oxygen because I want to make sure I hammer that message home. Air contains several gases, but it can be shown that when iron rusts, the gas that is used up is oxygen. Hence, iron rusts only when oxygen and water are both present. Water's role is to allow the flow of electrons to take place so that iron and oxygen can react, like an electrolyte in a cell. So the reaction will be written as iron, which is Fe, changes into oxygen, which is O2, becomes Fe2O3. Now, we're going to balance this equation because it's always good practice to balance your equations. If you've not done so, pause the video just now and try it. We start from the middle and look to the right. We've got 2 Fe's there and 1 Fe there, so I'm going to put a 2 at the front, just like so. I've got 3 oxygens there and 2 oxygens there. Now this does pose a problem, because if I put a 3 here, for example, to make that 6, that's going to knock off the number of irons. But to be honest, that's really what we have to do. We have to well, actually, there's one other thing we could do. We could go and turn this into 3 to match this side. The easiest way to do that is, if I divide 2 by 2, I get 1. And then if I times the 3 there, so 3 over 2, that would give me 3 oxygens at that side, because the 2's cancel out, and 3 oxygens there. I would then need to multiply everything by the denominator to make this work out. Okay, because it's bad practice to leave top-heavy fractions. So that would become 4 Fe plus 3 O2 arrow 2 Fe2O3. So what I've done there is I have multiplied everything by that denominator. So 2 times 2 gives me 4. 3 over 2 times 2, well, 2 divided by 2 is 1. So that would just become 3O2. And here we've got 1 there, so if I times that by 2, I get the 2 there. Now, please do not worry if you did not understand that, because what I just explained there is a very advanced way of working out formula. Okay, I'm going to show you another way which may be simpler to understand, and I would probably do that in this context, or expect you to do that in this context. So I'm going to rub this out, and I'm going to show you maybe an easier way to work it out. Okay, right. Now, here's an easier way. You've got that equation written down. Yeah, you could go and put a 2 there, right, for your FE, but then you're back to the same problem as what we had before. So why don't we start instead with the FE? Treat it like a puzzle, right? FE is not the best move at the start. Why don't we consider the oxygens? You've got a 3 there, and you've got a 2 there. There's a little trick called the cross-multiplying trick. Because that says 3, if I times that by 3, and then because that says 2, and I times that by 2, it makes everything easier to understand. Because, well, 2 times 3 gives me 6, and 2 times 3 gives me 6. So my oxygens are balanced. My ions, though, well, I've got 2 times 2, which is 4 here, but I've only got 1 here. But that's easy to solve because 1 times what gives me 4? Exactly, 4. So if I put the 4 there, I'm sorted. Okay, now you will probably have noticed that that is the exact same answer as what I got by trying to multiply out by using fractions. Okay, do not get yourself stressed about that. Treat it like it's a puzzle, and it's a puzzle that you can learn and get better at over time. But today's lesson is not focusing on that. If anybody needs support with it, you just need to get in touch with me, and I'll spend some time with you, give you some practice, give you some pointers, and I'll make sure you get up to speed. Okay, right, so let's move on. So it says corrosion is a chemical, well, that's obviously going to be reaction. Come on, hide. Corrosion is a chemical, oh, my pen's off again, reaction, which takes place in the surface of a metal. When the metal reacts with substances in the air, a new compound, to form a new compound. Since the metal is present in this compound as a metal ion, then the process of corrosion must involve the conversion of metal atoms into metal ions. Some metals, like sodium, corrode so fast that as soon as they are cut, the new pure sodium surface becomes dull. Watch some YouTube videos to see that, right? If you've not seen it in your class, it is incredible to see. The shiny surface of aluminium slowly becomes dull as the aluminium corrodes in the oxygen of the atmosphere to form aluminium oxide. Iron corrodes fairly fast, but much slower than sodium to form brown rust, which flakes.
Mommy and Daddy. Mommy and Daddy.
Sorry about that, that was my toddler interrupting me there. So iron corrodes fairly fast, but much slower than sodium, to form brown rust, which flakes off the surface, thus exposing more iron to the atmosphere. It then corrodes and, well, that probably would be flakes off. If you put falls, that's fine as well. Until eventually the iron is eaten away. An even slower reaction occurs when copper is exposed to the atmosphere. It corrodes in the oxygen and carbon dioxide to form green copper carbonate. Most metals corrode to some extent, but generally the higher the metal is in the electrochemical series, the faster it will corrode. The corrosion of iron is known as rusting. The term rusting applies only to iron. Metals corrode, but only iron rusts. That sentence is So many answers in the exams rely on that sentence, that metals corrode, but only iron rusts. There was a word bank there as well. I didn't use it. Lithium, potassium, sodium, well, you know they all react very fast. And they're stored under oil to prevent reaction with air and water. Magnesium, aluminium, zinc, iron, tin, copper rate of reaction decreases as you move down. And silver and gold don't react at all. Well, they don't corrode. So, a rust indicator. Ferroxyl indicator turns different colours in the presence of Fe2 plus ions and OH minus ions, factors which affect the rate of rusting. As rusting is a chemical reaction, then it is affected by the same factors that speed up other chemical reactions. If we know what speeds up a chemical reaction, all we need to do to reduce rusting is do the opposite. Temperature, well, an increase in temperature will increase the rate of rusting. For example, a car exhaust rusts more rapidly than the rest of the bodywork because of its higher temperature. Surface, small pieces of iron will rust faster or more quickly than a large lump of iron, since the small pieces have a higher surface area. Concentration. Iron exposed to low concentrations of oxygen will rust less than iron exposed to high concentrations of oxygen. For example, ships sunk in shallow seas will rust more quickly than ships lying at the bottom of deeper water because of the concentration of dissolved oxygen in seawater is greater near the surface. Carry out the following experiment into the presence of an electrolyte, salt in this case, on the speed of rusting. Well, the key here is that salt increases rusting. So the observation is, well, here we've got ferroxyl indicator and an iron nail. Just put in normal water. Well, it's going to rust, isn't it? So therefore, your ferroxyl will start off yellow. Actually starts yellow-green. And it changes to blue. But this one here, you'll see a faster colour change. And more blue. Because there is salt added in. And salt increases rusting. It increases the speed of rusting. The effect of electrolytes. Sodium chloride, salt, solution increases the rate of rusting. We already know that when iron rusts, the iron atoms lose electrons. And these electrons are transferred to the water and oxygen molecules. Sodium chloride is an ionic compound and its solution is an electrolyte. Like all electrolytes, sodium chloride solution contains ions which are free to move and so are able to conduct a current of electricity. The presence of these ions will therefore speed up transfer of electrons from the metal, which is talking about iron. Yeah, we're talking about iron. So therefore, from the iron to the water and oxygen molecules. If you've wrote metal to water and oxygen molecules, it's fine. And so increases the rate of rusting. This explains why the bodywork of cars rusts slower, not faster, sorry, because we're talking about salt, faster in winter than in summer. The salt in the roads in winter dissolves the rainwater, forming the electrolyte which speeds up the rusting process. Note, it is not just sodium chloride solution that speeds up the rusting process. Any ion containing solution, acids included, will accelerate the rusting of iron. When iron rusts, the iron atoms lose electrons to form iron II ions. Since both water and oxygen have to be present before rusting occurs, it must be the water and oxygen molecules which take the electrons away. So equation 1, well, we've started off with Fe, that's your iron, fresh iron, and it changes into Fe2. Well, ferroxyl turns blue in the presence of Fe2. So I'm going to put blue under there, and I advise you to do the same to jog your memory. In the presence of Fe2 plus, indicator turns from yellow-green to blue. It's more yellow with a wee tint of blue, more yellow with a wee tint of green, and then it turns blue. Fe2 plus changes into Fe3 plus electrons. Now, Fe3 plus does not react with ferroxyl indicator, only Fe2 it does. But as it's already changed blue, that blue colour does not disappear because it changes into Fe3 plus. Equations 1 and 2 are oxidation reactions. They are losing electrons. So another reaction must be taking place, a reduction reaction. So if something's losing electrons, something else must be gaining it. So if something's losing, undergoing oxidation, something must be gaining electrons, that's known as reduction. So we've got equation 3 here, and we've got water and oxygen and 4 electrons, changes into 4OH minus. Okay, now please note that I recommend that you learn equation 1 and equation 2 like it's a story. The story starts with iron, fresh iron that you've just bought, whether that be, I don't know, you've just bought a brand new car that's made up of Fe. When the paint has been chipped, rusting starts. That iron corrodes, it loses electrons. At first, it loses just 2 electrons in the very first reaction, and it forms Fe2+, which turns ferroxyl blue. That Fe2+ continues to react to form Fe3+. Why? Because rust is actually Fe2O3, which means that rust is made up of Fe3 plus ions. Why? Well, to get the formula here, you have to do the crossover method to get to here. The crossover method, well, oxygen is always in group 6, so has a valency of 2. Iron, well, it's a transition metal. So to get this formula, you had to cross them over. So iron would be Fe2, see where the 2 came from, and your O3 meant that 3 was the valency of this iron for this transition metal. That means that the end of our story, when we have rust, we have Fe3+. So this is the start of the story, that's the end of the story, that's the end of chapter 1, then chapter 2 continues with Fe2+ to get to the end, which is our rust ion. You have to remember equation 1 and equation 2. I suppose you could look them up in the data booklet, but because there is 3 equations for iron, it can get quite tricky. I think the easiest way to get the marks in the exam is just to remember equation 1 and equation 2 and just write down the only equation in the data booklet, which is about water and oxygen, and that's it there. In the presence of OH minus ions, ferroxyl indicator turns, well, ferroxyl indicator was yellow-green, remember? But in the presence of OH minus, it turns pink. The intensity of the blue colour, because we're talking about rusting here, so intensity of the blue gives an indication of the degree of rusting. The more intense the blue colour, the higher the concentration of, well, what ion causes ferroxyl to turn blue? Blue 2, Fe2. Then the higher the degree of rusting. Now this is the last bit that I'm going to do in the video. How to prevent or reduce rusting. Temperature. Temperature and surface are not always conditions that can be changed. There are two main forms of protection used. You can have physical protection, which is blocking access to the metal for oxygen and water, or electrochemical protection, which replaces any electrons that are lost so the metal cannot oxidize and form rust. Let's look at physical protection. Physical protection essentially is protecting the iron from water and oxygen. So here we've got a setup here. We've got the first nail just in water and ferroxyl indicator. The next one's coated in grease with ferroxyl indicator. The next one's been painted with correction fluid, aka Tipex and the like, you know. And the last one has been coated in plastic. All have been placed in water with ferroxyl indicator. Well, you've guessed it, the iron nail will rust. So you will see blue colour all over. Right, so the ferroxyl indicators turn blue. The one that's coated in grease, well, grease is going to block water because oil and water don't mix, and grease is just essentially very, very thick oil. So therefore, it's blocking the water. However, the bits that are exposed to the water will be blue. So blue colour where grease is not placed. Right, we all know this, that you can oil your chain of your bike, and wherever the oil isn't sitting, your chain will rust. Painted with correction fluid, again, that one's going to block water, and correction fluid's probably going to block oxygen as well. But again, wherever you have missed the paint, or wherever the paint's cracked, it's going to rust. So blue only where paint is absent. And the last one, plastic coating, well, again, it's going to block your water and oxygen, and it's going to be blue only where plastic is absent. Now, at home, you may have a dishwasher and the metal rack in your dishwasher is actually coated in plastic. What you should really not do in your dishwasher is place the knives in with the blade side down touching the plastic coating, because it's very easy to use a knife and cut the actual plastic coating off, exposing the iron rack, and so therefore causing your dishwasher rack to rust. And the last thing you want in your dishwasher is rust being formed, because it will stick to the sides of your stainless steel dishwasher, it'll stick to your plates and whatnot, and it'll just basically cause your dishwasher to generally get kind of ruined over time and dirty looking. You can actually recoat your dishwasher rack with some plastic. If iron is to rust, the surface must be in contact with both water and oxygen. If a coating is put on the surface of the iron, it will act as a barrier, cutting off the water I've made a mistake there, I'll fix that. Let's rub that out. So that's oxygen. Alright, so if a coating is put on the surface of the iron, then it will act as a barrier, cutting off the iron from the water and oxygen, preventing the iron from rusting. This method of physical protection used depends mainly on the size of the object to be protected and what it's used for. Examples of physical protection include painting, greasing, or plastic coating. Give examples of where you would benefit from iron being protected by these methods. Well, painting, you could paint cars, you can paint railings, you could paint your bike. Oil and grease, well, you could do your bike chain, you could do the moving engine parts. Plastic coating, your dishwasher rack, your tool handles, and there's probably other things that you can think of. There's a million things, but it's one of those situations that when you're asked to give examples when you're recording yourself, you can only think of a couple. Painting, electroplating, galvanizing, or tin plating. Electroplating is another example of physical protection. Galvanizing is where iron is plated with zinc. Iron is on the inside while zinc is on the outside. The zinc successfully blocks, well, it's going to block your water and oxygen from reaching the iron. Iron is found above or below zinc. Well, you've got to remember the phrase mass it. Well, there you go. There's your iron, there's your zinc. So it's found above the zinc, right? No, it's not. Oh dear, that's why I'm not reading it right. Try that again. So iron is found below the zinc on the electrochemical series. Therefore, if the zinc layer is scratched, the electrons will flow from the iron to the zinc. Remember that electrons always move from the top of the electrochemical series to the bottom. Unlike iron, whose oxide is red and flaky, the zinc reacts with oxygen to form zinc oxide, which is tough and fills the scratch, so no further corrosion should take place. How awesome is that? That if you have tin and you have zinc, and the zinc layer gets scratched, it actually forms zinc oxide and starts to fill in the gap. It makes zinc oxide, it's like a plaster that actually prevents the iron from rusting. Okay? I wrote tin there, but what I meant was that it's a tin made up of iron. Sorry to confuse you. Galvanizing is more expensive than tin plating. Food tins are often plated in tin. Tin prevents water and oxygen from reaching the iron core. However, tin is above or below iron, right? So there's your iron, right? So tin is actually below iron, right? This means that when scratched, the electrons flow from the iron to the tin. Okay, so just to make sure that we're on the same wavelength here, because I have caused some confusion, that if we've got galvanizing, when we've got galvanizing, the zinc gives electrons to the iron. The zinc forms zinc oxide that fills in the scratch and acts like a plaster, preventing further corrosion of the iron. The zinc gives electrons to the iron as well. So you've got two things happening with the galvanizing. You've got the physical protection, i.e. the plaster that stops further corrosion, but you've also got the electrochemical protection or the sacrificial protection where the zinc gives the iron electrons. Tin, that's not the case, because if tin is on the outside of an iron can is scratched, the iron in the middle will give electrons to the tin and so therefore corrode faster. This means that when scratched, electrons flow from the iron to the tin. Therefore, the tin is protected whilst the iron rusts. And then we've got some information about anodizing that you should have a little read about. Electrochemical protection, well, this is just the idea that I was telling you about, that the more reactive metal protects the less reactive metal by giving it electrons. So here we've got test tube, and these haven't been labelled. This should be test tube A, that should be test tube B, and that should be test tube C. In test tube A, well, we've just got a normal nail and water and peroxide indicator, so it's going to turn blue, isn't it? But this one, we've got it wrapped in magnesium, so we've got our masit metal. The magnesium is going to give electrons to the iron. So therefore, the iron cannot lose electrons, so the iron cannot undergo corrosion. The iron cannot rust. So therefore, no blue colour can be seen. In reality, what would happen is the magnesium would react with the water to form magnesium hydroxide. Form magnesium hydroxide. And when it forms magnesium hydroxide, you're getting the OH ions being produced. So therefore, actually, peroxyl would turn pink. And in this last one, we've got iron attached to copper. Well, remember, copper is actually below tin. So in this one, the iron is giving electrons to the copper. And so therefore, the iron's losing more electrons, it's losing them faster, and so therefore the iron will rust faster. So you'd actually see more blue colour than A. So attaching copper to iron is a really bad idea if you're wanting to save your iron. From these experiments, I can conclude that iron rusts faster if it's attached to copper. Iron rusts more slowly when it's attached to magnesium. In general, when the iron is in contact with a metal lower in the electrochemical series, it rusts more quickly. But when iron is in contact with a metal lower in the electrochemical series, the rusting process, In general, when the iron is in contact with a metal lower in the electrochemical series, rusts more quickly. Right, okay. When iron is in contact with a metal higher in the electrochemical series, the rusting process is slowed down. A closer look at what's going on. In this cell, the electrons flow from the magnesium to the iron nail because magnesium is above iron. No blue colour appears around the iron nail, and so no Fe2+ ions are being formed. Remember that peroxyl turns blue in the presence of Fe2. This means that iron nail hasn't rusted. In this cell, the electrons flow from, well, let's have a look. We've got iron and we've got copper. Where do the electrons flow from and to? Yep, the electrons go around this way, from the iron nail to the copper. And this one here, they went that way. Okay, so they're going to go from the iron to the copper. A blue colour appears around the iron nail, indicating that Fe2+ ions have been formed. This means that the iron nail has rusted. Sacrificial protection. Well, linking or attaching a metal which is more reactive or higher than iron in the electrochemical series will lead to sacrificial protection. Underground iron pipes can be protected from rusting using magnesium. Bags of magnesium are hung from the pipeline every 200 metres or so. Hulls of ships and oil rigs are protected by attaching blocks of zinc to them. Metals like magnesium and zinc are higher than iron in the electron series, and so will give their electrons to the iron, causing them to break up into ions. The solid metals are sacrificed to protect the iron. Cathodic protection. Cathodic protection is another form of electrochemical protection. Cathodic protection involves connecting the metal to the cathode of a battery. The cathode is protected. The cathode is the protected metal, i.e. the iron. The electrons pass to the iron, preventing the iron from rusting. Okay, now how that works is, remember, the cathode is negative. That's a V, sorry. Cathode is negative, the anode is positive. So what that means is, if you've got the cathode, right, so there's your power pack or battery or whatever, and you attach the nail to it, to the cathode side, now that would just be an electrode for the positive electrode. Remember, the cathode is negative. So the cathode, the negative side, this whole bit here, is pumping out electrons. So cathodic protection is basically where you take the metal that you want to protect and you attach it to a power supply that keeps giving it electrons. And so because you keep giving it electrons, it cannot lose electrons. And as corrosion is the oxidation reaction, the losing of electrons, because you're always giving it electrons, it can't lose electrons. And so therefore, Fe cannot change into Fe2+, because it keeps getting electrons, it cannot lose them. That's the idea of cathodic protection. Okay, that's all you need to know about it, that the metal cannot rust because you keep giving it electrons. So hopefully that's been helpful. If you need any more help, or if anything else needs to be explained, just let me know and I'll try and help you.